All right, so this is our last distribution that we're going to be talking about. We've dealt with binomial, we've dealt with normal, not only normal, standard normal, and now we're going to be doing Poisson distributions. A Poisson distribution is dealing with the probability that a certain thing will happen a certain amount of times in an interval. So it's deals with the number, excuse me. Some things that fall into this category, some examples, would be the number of meteors that strike the Earth in a year, the number of phone calls that come into a call center, the average number of fish that a fisherman catches. These are things that happen a certain number of times on average in a time interval, okay? So we could say that on average there are, say, 1,000 meteors, you know, some of them are small, that strike the Earth every year, okay? That's an average, all right? And this is talking about what are the odds of more than that, or less than that, or, you know, how many events are going to occur if we expect an average amount to happen in that same interval. All right, so let's start off with an example. Well, first of all, let's start off with the formula for them. Don't ask me how the man came up with this formula. I think he was a necromancer. All right, the probability of x is equal to let me explain. All right, now, by the way, 1 second. IB writes the formula slightly differently. That's right. All right, the only difference is, excuse me, sir, IB uses M instead of lambda. The rest of the world uses lambda. And IB and several other textbooks and resources that I've looked at leave the exponential in the numerator with a negative exponent. I don't see a reason why. Okay, so let me explain what these all are. X is the number of events. Lambda is the average number of events. And obviously E is the exponential. So a couple of things to point out. What do we know about the number x? What kind of values can we expect to see for the values of x? Can we expect a fraction for x? No, why not? How do you know that it can't be a fraction? Which one? Yeah, you can't have half of an event. And you also can't have decimal or fractions in factorial, okay? So factorials only take in whole numbers. But x can be 0, all right? So it's not just the integers, it's 0 included, so the whole numbers. Because you can say, well, you know, if the average number of fish that a fisherman catches is, say, 1.2 fish per hour, well, there is the possibility that he gets no fish. So 0 could be something that you're using, okay? All right. So, make sure everyone has this guy copied. Okay. Cool. All right. Now, a traffic light All right. So, traffic light automatically photographs a red light violations on average once per hour. Okay. Now, it's important to point out that just because, I mean, this falls into a Poisson distribution because the events have nothing to do with each other. You know, if one person runs a red light, it has nothing to do with the probability that somebody will run a red light next hour or 10 minutes down the road or a minute down the road. Okay, so they're independent events. And what we're going to be dealing with now are looking at the probabilities of more than that number or less than that number, or however, what are the probabilities that some rare event is going to happen? Okay, like we could use this kind of a distribution to say, what is the probability that 40 photographs will be taken? Okay, it's obviously going to be a small number in this unusual example that I give, but this is how we find those rare kind of probabilities. Okay, all right, so the question would be, so we have these three questions to ask. All right, so the first thing that we have to come up with is, what is the average that we expect? So if we have a 10-minute interval, what is the probability that one photograph occurs? Well, first thing we have to find out is, what is the expected number of photographs that it should take in that 10 minutes? How much? 1/6, okay? The average is going to be 1/6. It'll take 1/6 of a photograph in 10, obviously that, we're talking about an average here, but it's important to do that first. Sometimes it's given to you, sometimes it's straight up, and you just put it right in the equation, and you're happy, wonderful. Other times, you have to figure out what that number would be. Okay? All right, so now we can do this straight ahead. It's a straight plugging chug problem. So the probability of x being 1 is going to be 1/6 with one event, e to the 1/6, 1 factorial. And obviously that's going to be a calculator job. And we know that 1 factorial is 1, 1/6 to the 1 is 1/6, And now we have to calculate what e to the negative 1/6 power is. Go ahead and crunch that, please. The E button on the calculator? It's on the left where it's shift natural log. What value are you coming up with? How much? 0.141 is what I'm getting. Remember 3 sig figs. Okay. Yeah. Yeah, you need to divide by e to the 1. Yeah, so it's 1/6 divided by e to the 1/6. There you go. All right. B, x equals 2. Well, now we're just changing our exponents. Yes? Because it's an approximation. You know, I am rounding. Yeah. Okay. And it's always good to know, to be able to do some algebraic manipulation of this thing, okay? Because sometimes I might be asking you a question where you have to do some algebra with this equation, rather than just crunch a number and get it out of your calculator. Okay? We cool? All right. So crunching that. Is everyone getting... Remember, 3 sig figs, right? Is that what y'all got? Okay, good. All right. And finally, at least one photo. So now, what we're dealing with is the probability of being 1, 2, 3, 4, 5. I mean, there are a lot of probability. I mean, granted, the probability of it being 10 photographs in that 10-minute period is pretty small. And in fact, we would probably run into, you know, in real life, we would run into upper limits of this, you know, how much traffic goes through the light. I mean, obviously, if we can't have 5,000 photographs, that wouldn't make sense. But in another circumstance, you would imagine that, you know, we could be dealing with a problem that does allow infinite answers, okay? But we're going to take this one as it is and say, all right, we're going to allow that. But what does it mean when it says at least one photo? What's another way of writing that? Greater than or equal to 1. Okay, cool. All right. So really what we're saying is x is greater than or equal to 1. All right. But what's another easier way to do that? It's true. But what do I don't want? At least 1. 1 is good. I'm allowing 1. But what do I not want? Yeah, I don't want 0. Okay? So in reality, this is probably done a lot easier by finding out what the probability is for 0 events and saying, hey, that's not allowed. We're going to subtract that. Okay? Start with 100% probability and say, take away the 1 value that I'm not allowing. Okay? So that's probably easier. See? 1 minus the probability of 0 events. And that would be 1/6 to the 0th, e to the 0th, sorry, e to the 1/6, I'm sorry. And what is 0 factorial? 1. It's defined as 1. Okay. So now we can crunch that. Is that what is everyone getting? Are we cool? Yeah, approximately. Approximately. Yeah, squiggly lines is approximately 1.54. Okay. Now, I'm going to amend the question, throw another one at you, and say at least 3. Actually, can I change it again? At most 3. Because at that point, maybe the machine runs out of film, or the machine runs out of memory space, or it can't handle it for some reason, and that's like my upper limit, okay? And we could say, well, you know, that's, you know, it's a pretty good machine, but it's not perfect, and because, you know, like let's just say you work for a municipality and you have to decide, well, which camera are we going to buy? We can buy this really expensive camera that can take an infinite number of photographs, or we can buy this really cheap camera that is okay as long as you don't have 4 photographs in a 10-minute period. Okay? Well, you could say, well, what are the odds that I'm actually going to have 4 events in a 10-minute period? Well, that's kind of what we're dealing with here. So when we say at most 3, what scenarios are we talking about? 0, 1, 2, and 3. All of those are allowed options. Okay? So we could do the 4 calculations. Do it for 0, do it for 1, do it for 2, do it for 3, and then be done. Right? Well, lucky for us, we've already done 0, 1, 2. Well, we can find 0 by subtracting 1.54 from 1 again and get it back. But we also have this fancy-dancy thing called a calculator. All right. So hit math. Oh, sorry, second distribution. Go to second distribution. And I do believe you will see second distribution, and if you scroll, there it is, PDF and CDF. Poisson PDF and Poisson CDF. Okay, now, just for our sake, I'm going to redo one of these problems using this command to make sure that we actually did it correctly. So, 1/6. And let's do the first one. And that is the answer that we got for part A of this question. Calm down. All right. So this will, the PDF gives me a specific single individual value. Okay. Gentlemen, behave yourselves. CDF, like all the other cumulative density, cumulative distribution functions that we've done, adds up everybody. Okay? So for this one, we will do CDF 1/6, and the x value that I'm interested in is the upper limit, 3. And we're good 99.997% of the time. Okay? So the odds of it being more than 3 is pretty darn small. Yeah, because I'm going 0, 1, 2, and 3. I'm accumulating up to 3. Okay? Yes?
So for A and B, PDF.
PDFs for A and B, yes.
For C and B.
Well, for C, you're really just taking one value out. So you would use a PDF and do 1 minus the PDF. Okay. Yes. Okay. We're cool? All right. A couple of quick other things about this. We'll do a similar example. Okay, so let's say that a fisherman has an average rate of 0.667 fish per hour. Fish caught per hour. Okay. So if the guy goes out and fishes for 7 hours straight, okay, what are the odds that he will catch, well, 1 fish, 2 fish, 3 fish, 4 fish, and any number of fish that we're asking for? So one thing that I might ask you and would be reasonable to expect is to, excuse me, find a function that I could just plug numbers into, and it would spit out the values for this guy fishing. All right? All right, well, the first place that you might want to look is the equation. We already have one equation. So going back here, well, this is fine because it's the x that we're going to be feeding it, right? However many fish he catches. But what's my lambda? Well, how many fish should he expect? I mean, what are his odds now? Because he normally catches about 2/3 of a fish every hour. But if he's out there for 7 hours, you would expect that he's going to come back with something, right? You know, every hour, well, let's put it this way, every 3 hours he'll probably come back with 2 fish, roughly speaking, right? Well, how are we going to find out what is the expected number of fish in a 7-hour period? Yeah, multiply it, right. So 0.667 times 7 4.667 times 7, 4.669. Okay? So we can expect him to come back with 4.669 fish. Okay? Which, by the way, brings up an important point. The expectation value of a Poisson distribution is the average. Point that out. Let me write that in there. Is equal to my average. Because that's really what the expectation value is. The expectation value is, what do you expect? Well, on average, in the long run, over the long haul, it's going to be the average. So conceptually, it kind of makes sense. Okay? All right. So now, all we're really doing is plugging things in and getting an equation out of this. So the one that I'm looking for is 4.669 to the x all over e to the 4.669 x factorial. And that would be the equation that would give you any probability you wanted. If I asked you to make a table, you could use this to make that table. Okay? We would be able to use lists to make this table. Okay? All right. I'm going to spare us all the arduous process of making that list, and Melanie, for who's now watching this video, and say, okay, everyone say goodbye, Melanie.
Bye, Melanie.
This episode of The Ronco Show has been brought to you by the Poisson distribution.